Hello and welcome to the channel. Today we're going to be talking about behavior cloning in LIBERO. So LIBERO is this robotics library that has a series of different environments with a bunch of different tasks, different robots, and then importantly, it ships with quite a bit of human data that we can use for training. So this makes it a lot easier for us to get up and running quickly because you don't have to clone or you don't have to generate a bunch of your own data for behavior cloning in a robot. And let's talk about what behavior cloning is and then what we're going to try to accomplish in this video. So behavior cloning is kind of what it sounds like. It's providing human demonstration data. So, a human piloting the robot for some number of times and then getting the robot to follow those examples by itself. That is the root of what behavior cloning is. And in this video, we're going to build up an algorithm from scratch to do behavior cloning with data provided as part of the LIBERO library. And we're going to take a simplified approach. So this won't be a full production grade implementation. It'll be running through how to get, the LIBERO library. I will provide some bootstrapping files for you to get started. And then we're just going to go and get one task working. So let's get started. If we go to the LIBERO GitHub page, and I will throw this in the video description, the first thing you need to do is install it. And this is assuming that you already have Anaconda up and running. I'm also making the assumption that you have Linux. I don't know how much of this will work on Windows. You can certainly try, and I welcome you to do so. You're just following a different process than I am, potentially. But all of this looks Windows friendly. So follow through the installation here. I'm not going to rerun it because I've already done it. Go ahead and do a conda create, conda activate LIBERO, git clone, cd, pip install requirements, and then the pip install -e. That is going to land you with something like this. So you're going to have a LIBERO folder that has all of your, all of the library information. It's going to have some demos. It'll have, there won't be anything from data sets right off the bat. All right. So I have data sets, obviously, because I've already downloaded them. So once you've gone through the conda install, run the pip install. And then we want to go ahead and grab the data sets. So you can literally just run this Python benchmark scripts, download LIBERO datasets, and it's going to go and download about 35 gigs of data. So that will take a little while. You can obviously pass in a use Hugging Face flag if you want to pull from there. This one I've noticed works, but it does give an error saying that the original URLs will eventually be deprecated. But just so you know, this is what I ran. So run through the installation. When you have LIBERO installed, we'll pick up and go from there. So start that, and then we're going to flip over to my repo. So to help you get started, I have put together a few different pieces of code here. The data loader, and that is going to grab the data set, do a little bit of observation tweaking, and return this in a few different variables here. So we're going to get an agent view camera, a wrist camera, a joint state, and then the actions taken in that state. And this is something that I didn't consider core to the algorithm. This is just, getting the data in a format that you can use it. So this is our data loader.py. I included an env wrapper. So this is going to include some image processing. I am concatenating joint state. So the two of the things that it has are joint position and gripper position. And actually, we're not even using joint state in this algorithm. I never had to use it. So we're throwing some of this data away, but I wanted it there for future work. It just ended up not being needed. I fully expected joint state to need to be passed in to make this work. Then we've got a render method, which you'll notice I'm having to reach to inside of the environment to find a render. So this is where we can actually watch it on screen. We're going to have a reset, set init state, step, seed, and close, which we'll call self-env close. And I'm going kind of fast because these are the portions that you just kind of get for free. And I assume that you're currently downloading and setting up the environment while I'm talking, so why not? The last thing you're going to get is a requirements.txt. So there is a little bit of environmental overlap here in that this is going to install Python 3.8.13 and some older Torch versions, which is what they recommend. And then we are going to actually need, assuming you have an NVIDIA GPU, we are going to need a newer version of Python in order to get a version of CUDA that runs on newer NVIDIA GPUs. If you're running AMD, you might need to play with ROCm. But what I've done here is thrown together a requirements.txt that can be installed after you have done this LIBERO setup in a second environment. So what does that look like? Well, what I ended up doing is I ended up running a conda create LIBERO modern. So this is the first time I'm showing something on my screen that you actually need to do. So if we look at, I'll blow up the text here, look at what I've got here. So conda create -n LIBERO modern Python 3.10.20. That is the base that you want to actually use. So we're going to create a LIBERO environment that is following their installation instructions to get LIBERO installed on your machine. And then we're going to create a LIBERO modern environment that has the latest version of, or not the latest version of Python, that has a version of Python that is both compatible with the older LIBERO code and with the newer PyTorch code. So create that. I could run it, but it's saying remove existing environment, which I don't want to do. I've already got an environment set up. Once you have that up and running, go ahead and clone down my simple behavior cloning with LIBERO repo. That's going to be your starter. That's where we're kicking things off. Conda activate LIBERO-modern, our newly created LIBERO environment. And then go ahead and pip install -r requirements.txt. And everything should be fine for me because I've already got all the packages. But that's going to set you up to have something, ready to go to actually start writing code with that will be, functional. Okay. Again, I know I blew past the environment setup kind of quickly, but if you were able to follow through that, at this point you have LIBERO set up based on the install guide on their page. You have my demo project, and you are ready to start writing code. So something I'm going to do, just because I want to keep that repo nice and clean, I'm going to copy YouTube simple behavior cloning to just I'll do it this way. YouTube simple behavior cloning, and then remove the YouTube. Okay. And then this is not something you need to do, but I need to grab my build.sh. And build.sh is just how I'm set up with NeoVim. So you don't need to know a whole lot about this. This is just sourcing Conda, activating LIBERO modern, and then kicking off whichever script I feel like running. All right, so we are going to start off with train.py. And let's go ahead and create a train.py. And let's also create an agent.py. And we'll talk about the way these are going to be structured. So I like to create an agent class that kind of manages everything else. So my agent class is going to have the initial data load set up in its own init. It's going to initialize the models. It's going to initialize, devices. And then the agent class will have a train method and a test method. And those will be run by my train.py and test.py. So train.py and test.py will both have very little actual logic in them. They'll basically just be scripts that call agent, and agent will have all of that logic. So let's go ahead and start to implement our agent class. And for now, we will get the data loader going. So we'll do class agent and then def init. And the things that we'll need here are self. We're going to have an eval parameter that defaults to false. And then we'll have a learning rate, which will be 0.0001. Okay. Our dataset file name, so the task that we're going to pick up and attempt to clone. And this is kind of a long one. It's called pick underscore. In fact, I'm not even going to narrate the underscores because there are going to be a bunch of them. Pick up the black bowl between the plate and the ramekin, if I'm saying that correctly. And place it on the plate demo.hdf5. Okay, so that's kind of long, and we want to make sure that we actually got it right. I guess I could have just had you copy it to begin with. That probably would have been better. But if we come in here to where we downloaded Libero, and we go to datasets, and I'll demystify this a little bit. If we go over to data loader here, we're calling dataset file on os.path.join get libero path datasets libero spatial and then dataset file name. So we can come over here to libero spatial. Helps if I actually cd into it. And I should be able to ls on the name that we just typed. And there we go. So I did type it correctly. So you'll want to come over here and just make sure that you got that very large file name the way we intended to have it. Okay, self.dl. And we are going to need the data loader class. So up here at the top, let's do from data loader import data loader. And then here we'll do self.dl is equal to data loader, and dataset file name is equal to dataset file name. So we're just passing that into our data loader. And this will go and do, a full load of the data and make it available to us. So I like to test as we go. So let's come in here, and this is the minimum testable piece of code. So let's do from in train.py, if you didn't notice what file I went to, from agent import agent. And then we can say agent equals agent. And I think, let's go see exactly what we said. We said eval and learning rate. So we can actually leave those default. And then that's it. Let's run it. So this should pull in our data loader, and it is working. So if you get any errors at this stage, there's either something wrong with, you've got a path wrong, the data didn't get loaded correctly, or Libero didn't get loaded correctly. And this would be a good time to stop and fix the environment before you go any further into the code. Okay. We also want to go ahead and do some imports here from env wrapper, import Libero obs wrapper. So that's our observation wrapper. And then we'll do import torch.nn.functional as f. We'll need that. And then we'll need to go and pull a few things from Libero itself. So we're going to redirect some of the standard error messages because it's going to alert on things that are out of date that we really can't fix without, forking Libero and doing some cleanup. Or at minimum, if there's a better way to fix them, I haven't found it yet. So with context_lib.redirect stderr standard error io.string.io and then here, we probably need to go grab context_lib. Yeah, we do. I'm missing a few imports here. I had scrolled down too far. Okay, let's import context_lib, import io, import os, and import torch. Okay, that might be everything. We'll find out. So now inside of this with context_lib redirect stdr, we're going to say from libero import benchmark get libero path. From libero.envs import off-screen render env. And then from libero.envs.env wrapper import control env. Okay. All of that looks good. Okay. Let's go ahead and grab our task suite. So we're going to say task suite is benchmark.get benchmark dict. And then we're going to grab Libero spatial with parentheses at the end. Task equals task suite dot get task 0. And then task BDDL is os.path.join and get Libero path BDDL files task.problem helps if I spell task .problem folder task.bddl file. Okay. And since I didn't really explain that, BDDL files, I believe, stand for behavioral description something. They're basically like a task definition file for Libero, if I understand them correctly. Okay. We need to go ahead and set our eval parameter. So self.eval is equal to eval. And then we will start using that eval parameter, and we're going to declare our environment that we're playing in. So we'll say if self.eval, then self.env is equal to control env. And just to, it's probably better if I define the else so it makes sense what we're doing here. So when eval is true, we want to be able to see the robot doing something. Like we want to see it on our screen. When eval is false, we're obviously in training and we don't want to see it trying to render while it's trying to train. We just want it to train as quickly as possible. So here we can say self.env is equal to off-screen render env. And then we can say bddl file name is equal to task bddl. Camera heights is equal to 128. Camera width is equal to 128, and close it out. So off-screen render env, if I remember correctly, is a wrapper for control env that handles off-screen rendering. We don't need off-screen rendering for env or for our env in eval mode. So here we can say bddl file name is equal to task bddl, just like before. Has renderer, in this case, will be true. Has off-screen renderer will also be true. Use camera obs will be true. Render camera is equal to agent view. And I want to say this off-screen render env covers the has off-screen renderer equals true and use camera obs equals true. They're just defaults when you use that one. Now that we've created these, we need to say self.env.seed. We'll set it to 0. And then self.env equals libero obs wrapper. So that's our observation wrapper that you downloaded with git clone. And we'll do self.env. So we're creating either a control env or an off-screen render env, depending on whether we're evaluating. And then we are wrapping that in our own wrapper so that it will work more easily with this algorithm. All right. Let's go ahead and give ourselves a device. So we'll do self.device is equal to CUDA 0 if torch.CUDA.is available, else CPU. Okay, and then let's just run this and make sure that there are no errors, and there are not. Okay, before we go any further, it's time to go ahead and start setting up our model. And behavior cloning, at least the method we're using, is going to be relatively simple. We're going to have a basic 3 convolutional layers that will take an image and pull that image in and process it down. We're going to flatten it, and then we're going to have 2 linear layers and an output layer. That output layer will have an output that is 7 wide because there are 7 actions. It's a continuous action space with 7 actions. And then we will be, piping that directly into the move commands for the robot. So it's going to be simple enough. So we will create a model.py and start building. So in model.py, we need torch. We need torch.nn as nn. We need torch.nn.functional as f. And then we need OS. We'll be using that for some directory creation. Okay, we need a weights init. Let me make sure I'm actually using. Okay, yes. We need a weights init. So that's weights underscore init underscore, and then m as our parameter. If is instance m of nn.linear. So if it's a linear layer, then we want to use a torch.nn.init.xavier uniform m.weight. Oh, got my keyboard in a weird mode there. There we go, back to normal. m.weight, and a gain of 1, and torch.nn.init.constant m.bias and 0. And what this block of code is basically doing is starting us with a standardized, Xavier uniform distribution of weights for the model, instead of letting the model just initialize completely randomly. And if I'm being honest, I have copied this code across so many implementations now that I don't remember the specific driver for Xavier uniform. I know that it tends to stabilize my projects, and I will continue to use it until I find something better. So no deep reasoning there. We're going to do class model, and it will inherit from nn.module. And this one will take a few more values. So we're going to do our init method, and that will take self, input shape, num actions, hidden dim, checkpoint dir. It also occurs to me that it would be better if I zoomed in even more. Hopefully that's better for you. Checkpoint dir will be equal to checkpoints, and name will be BC network. Okay. We'll call super with model self init, and then we'll get into defining our actual layers. So our layers here will be self.conv1 equals nn.conv2d. Input shape will be, we'll grab the 0th element of input shape. 32 will be our first convolutional layer. Kernel size will be 8. Stride will be 4. And then we're just going to copy this to conv2. And when you're doing convolutional layers, the number of channels here, so we're going from 32 on the last image, so that 32 needs to line up with the input here. So you can think of this as an output, this is an input. So we're feeding 32 channels into an input of 32. We're going to feed that into an output of 64. Kernel size will go down as we go. So we'll change kernel size to 4 on this one. And stride will be 2. We'll go ahead and copy this again to conv3. And here, again, we need to match, so 64 kernels. This time we'll leave the output at 64 as well. Kernel size will be 3, and stride will be 1. Okay. Now we are actually going to need to know the output size of our convolutional layers in order to pass that into the next layer. We can figure that out mathematically and just step through the formula, but I actually prefer to do this programmatically and just make the layer tell us how big it is. So how do we do that? So let's package up our convolutional forward pass like this. So we're going to say def underscore conv underscore forward, and we'll take self and x, and then we're just going to pass x through f.relu and self.conv1 x, and we will do that 3 more times. 2, 3, and then we're just going to return x.flatten and 1. So that's our conv layer. So how do we use it? We can say with torch.nograd, because we don't want to take this into account during backpropagation. We're going to create a dummy vector. So that'll be torch.zeros, and that'll be 1, and unpack our input shape. And then our flat size is going to be self._com forward, dummy, dot shape, and 1. So what did we just do? We just did the exact same path that we will take in active use, passed a dummy vector through our com forward method, and got the flat size on the other end of that dynamically instead of having to compute it. And the cool thing about doing it this way, other than we get to be lazy and not have to do math, is now if I change something, if I change this from 64 to 128, or if I decide to try these all at 32 or something like that, this is going to automatically figure out that output size for me, so we don't have to adjust anything, which I feel like is enough of a reason to do this. So now that we have our flat size, we can just say self.linear1 is equal to nn.linear, and we can say flat size is our input, and our hidden dim, oh, I had an extra underscore instead of a comma. That was going to cause us some problems. And then we can say self.linear2 will be equal to nn.linear hidden dim. And then self.output will be equal to nn.linear hidden dim and num actions. Okay. A few other things we need to define. We need to set self.name will be name. We'll be using that later in the save methods. Self.checkpoint dir will be checkpoint dir, and self.checkpoint file will be os.path.join self.checkpointdir and name. And then finally, for our init method, we will say os.makeDirs self.checkpointdir, and we will say that it's okay, so exist okay equals true. So don't fail if it's already there. And then we'll do self.apply and apply our weights init that we defined up here. There is no parentheses after weights init. Okay, that's our entire model init method. Now we just have to define our forward method, or our forward method and our two save methods. So forward is pretty simple. We've written most of the code. So now we need to do def forward, self and x equals self._conv forward. Because we've already written all that, there's no reason to redo it. We do need to take joint state. Again, we're not going to use it, but I've got it in there for if a more advanced algorithm or a harder problem ends up needing it. When I started this project, I expected to need both and then just didn't. So for the purposes of this very quick, behavior cloning YouTube video, wasn't necessary to build that up. So let's go ahead and do x equals f.relu self.linear1 and pass in x. And then we can copy and paste that and do self.linear2 and copy and paste it a third time and do self.output. And then finally we can return x. And that's our whole forward method. So this is enough to train. All we need now in here are our save and load methods. And you can call torch.stateDict, like you could do this external to the model. I really like these little quality of life improvements, to just be able to call a save checkpoint on the model itself and not have to manage that externally. So we're going to say def save checkpoint self, and we'll call torch.save self.stateDict self.checkpointFile. Okay, and that is our entire save method. And then we will also do a def load checkpoint self and self.loadStateDict torch.load self.checkpointFile. And that's it. That is our whole model class, and we are ready to go implement it. And you'll notice that there's nothing there's nothing special about this model class. If you've done any kind of Q-learning or any soft actor critic, DDPG, like this is a very basic model. We've got 3 convolutional layers to pick up an image and process it. We've got 2 linear layers. We've got an output layer. And that's, we're dropping 7 outputs. And I just realized that I have a bug that would have bitten us later. So wrapping self.output in f.relu is not correct. Because remember, relu is rectified linear units. So relu is going to drop off everything below. This is worth spending 2 seconds on and just explaining. So if you were to pass a 1.2 into a relu function, the return would be 1.2. Easy, right? Relu cuts off everything under 0. So if you were to pass a negative 1.2 into relu, it's going to return 0. So what we actually need is a tanh function, and tanh is going to clamp us to between -1 and +1, which is what we actually want, because the robot joints are going to take actions applied between -1 and 1. So relu is wrong for this last one. The correct activation function is tanh. Okay. Now that we've got our model, it is time to go back over to agent. And I'm just pulling this up on my other screen as well. Okay, so under device, we've defined device. We now need self.model. Oh, and it would help if we actually went up to the top here and imported our model. So from model, import model. And just needed to restart Pyrite to get it to pick up that model was in fact a real thing. Okay, so self.model is equal to model, and we will be passing an input shape of 3, 128, 128. We'll be passing in num actions is equal to 7. And we will be using a hidden dim of 256. So these don't need to be particularly large networks. 256 parameters is plenty to train this successfully. And then we will send this to self.device. We'll set an optimizer. We're going to use Atom. So self.optimizer is equal to torch.optim.atom. And here we will do self.model.parameters. And then we will set our learning rate, LR, equal to our own LR variable. Okay. And for whatever reason, Pyrite is telling me that Atom is not exported, and I happen to know that it is. And then in my version, I've got some logging code, but I don't actually think we need it. So we're just going to say image joint state is equal to self.env.reset, and that just resets the environment. Okay, So let's run all this and just make sure we don't hit any errors. And we do not. Oh, hang on. Yes, we do. We do, in fact, hit errors. Oh, I know what's happening. So if you get this EGL error, what that basically means is that the environment did not close cleanly. And unfortunately, because it throws this big mess of errors anytime the environment doesn't close cleanly, it also makes it kind of hard to see your real errors when those real errors happen. To at least get this to go away on a good run, something we can do is we can go ahead and implement a close method. So this is simple enough. Def close self and call self.env.close. And then over here in train.py, we can just say agent.close. And now we get a successful process exited without the big ugly error. But again, if it dies somewhere in between, we will still get that error. It'll just be, below whatever the real issue was. So it does make things kind of painful to find. All right, now we get into the fun part. And after everything we've built up, the model training is actually pretty simple. So we're going to define a train. I'll just go one more down. So we have our train method, and we will need self epochs, so the number of training epochs we're going to use, and batch size. We will have lowest loss is equal to 100. Let me just close this down here. And I want to create myself some space. I've got some weird terminal flickering going on there that I think is Pyrite doing things. So we're going to say for I in range epochs. I'm going to disable a plugin and see if that helps. Hold on. All right, let's see if things get any better. That weird flickering issue. Apologies for not catching it earlier. I'm bouncing between screens and didn't notice the flicker, really. Okay, so for I in range epochs. So the first thing we're going to do is grab our batch from self.dl.getBatch, and batch size will be batch size. So we're grabbing a batch of training data. And then we need to break that out into images, joint states, and actions. So we're going to say images is equal to batch and agent view. And then we'll send that to self.device. Joint states will be equal to batch. Actually, let's do single quotes there. I don't have a particular reason to, it just looks better. Okay, and joint state dot to self.device, and actions is equal to batch actions dot to self.device. Okay, so we've got our batches of joints, actions, and images. And at its core, behavior cloning is simple. What we're trying to say when we do behavior cloning is that the robot should do what the human did in the demonstration data. So all we need to do to get our loss function is get an action prediction. So we're going to say action pred. So what are our predicted actions from self.model, and call images and joint states. And then our loss function is just the difference between actions and predicted actions. So we can say loss is equal to f.l1 loss actions pred. And let's be consistent. I said action. Let's make it actions in both places. Will be plural. And then we just have to do a self.optimizer.zero grad loss.backward self.optimizer.step. And that's the whole training function. That's it. So if it felt like I was kind of speeding through everything else, it was to get here. It was to get to the point of showing you that all a basic behavior cloning algorithm has to be, if you've got good data and you've set everything up correctly in the environment, and fortunately, good data is something that this library is just kind of giving us out of the box. But once you've got that, the algorithm to do simple behavior cloning is not all that complicated. Now we'll just do some debug logging, which will be almost as much code as the actual learning. So we'll say if I modulo 100 is equal to 0, then print episode I loss.item. And then we'll just say if loss.item is less than lowest loss. So that's where our lowest loss comes into play, is basically if loss goes under a certain amount, we want to save the model. So we'll set lowest loss equal to loss.item. And if you're not familiar with loss.item, that basically just gives you a number for loss. So loss is normally a tensor. It's got all the gradient information bundled up in it. And if you say loss.item, then you're just getting the raw number out of that. So we can finally say self.model.save checkpoint and print f. We'll do a new line, saved checkpoint at episode I, and then another new line. And that's the whole training method. So let's come over here to train.py and call agent.train. And let's run it. And worth noting, I am using the same computer to record that I'm using to run this. If things get a little choppy while the GPU is under load, that could be the problem. Okay, we are missing a couple of parameters. GPU won't go under load if I don't actually plug in the right things to run it. That would help. So we're going to do epochs. Let's start with 10,000, and batch size is equal to 32. Okay, so what we see here is very, very quickly, we started with a loss of 0.31 roughly, and we are already down to a loss of 0.10 and 0.11, and it's kind of bouncing around a little bit. So we're going to let that sit there and run, and we are going to build out the test method, because that is our final thing to do, and then this whole project is complete. So test method is all about display. It's all about seeing something run. So we'll say def test self. We will load the checkpoint. So self.model.load checkpoint, self.model.eval, and that's just throwing the model in eval mode. We will grab our image and joint state from self. Oh, I didn't need to type from, I just needed to say it, from self.env.reset. And then we're just going to do a loop. So for I in range 3000, which is a number I picked out of thin air, with torch.noGrad, because we don't need to calculate gradients for any of this. We will grab img t torch.asTensor image device is stay. Device is equal to self.device.unsqueeze on the 0th dimension. And all we're doing here is grabbing our images and joint states and throwing them in as tensors. Okay, we'll pass in joint state. And then we will pass both of those to the model. So we're going to get action is equal to self.model and imgt and jst. You can call these whatever you want as long as they don't overlap. And then we'll do action is equal to action.squeeze 0.cpu.numpy. Throw it on the CPU and then turn it into a NumPy array instead of a PyTorch tensor. And then finally, we will actually take an env step. So image and joint state, this is what we get back from our environment. Reward, which we aren't actually using, done info is equal to self.env.step and action. In order to see it, we need to call self.env.render. And then if done, print success at step I and break. Okay. And then we need a test.py. So our model finished after 10,000 epochs with a loss right around, looks like the lowest was this 0.0415, et cetera, et cetera. So now we just need to do test.py. And our test.py, just like our train.py, is going to be pretty simple. We will do from agent, import agent. Agent will be agent with eval equals true this time. And then we'll do agent.test and agent.close. All right, so this is our big moment to see how it does. I'm going to cut build.sh over to my build.sh over to calling test.py. In whatever editor you're using, just run test.py. And let's see what we get. Ooh, we've got our robot arm. It's picking up a cup. It's doing something. All right, and it got stuck. We failed. Okay, that's fine. Let's go back and let's train a little bit more. We can tell that it's starting to understand what to do, but that it hasn't quite gotten there. So let's raise it to 50,000 epochs. And I will have to move build.sh back over to train. Okay, so now we're going to run with 50,000 epochs, and we'll see how low we can get loss. I'm going to pause for a moment so you're not just watching this. All right, checking back in around 20,000. I don't want to interrupt training, but what we can do is I can come over here and conda activate libero modern, and then just run test.py, and let's see how it's doing. Around 20,000 epochs. All right, we're picking up the bowl, and we're trying to get it onto the plate, but we're not quite there. And now we're stuck. Okay, 20,000 was not enough is the answer. And our loss is still going down at 24,000. I'm actually curious. When I did this the first time, I ran it for a full 100,000 and, just walked away for a bit. Okay, we're still not quite there. Still just trying. But our arm is making progress. Something that jumps out at me about this method of training over using things like reinforcement learning is just how smooth it is. Because if you've done any RL or if you've watched any of my reinforcement learning videos where, a robot is basically trained to do something by itself just based on the environment reward, it tends to be very jumpy, very shaky. And it's because the thing that it's optimizing for is just getting to the goal. It has no concept of smoothness unless you figure out how to build that into the loss function. It's just going to, try to find whatever it's doing somewhat aggressively. And it definitely looks that way. Hey, that was pretty good. 0.008. So what I notice here using behavior cloning is because it's following human demos, and those humans attempted to, I assume, do the task smoothly, because we do have a concept of not just lurching towards a goal. What you end up with is something that is much, much more pleasant just to watch and to interact with. Okay. So if you recall, we're right around 37,000 epochs now, and we are picking up the bowl and almost getting it onto the plate, but not quite. We tried. Okay. We're at 39. I may need to go back and do the 100,000 epochs. And if I do, I will pause the video and not make you watch all that. Unfortunately, I can't change it midway through. So your takeaway should be, if you're watching the same thing I am, maybe throw 100,000 at it and go have lunch. Okay, so we just got a new low at 43,000 and 44,000. You'll notice that there's not much ground left to gain on our loss. We're getting increasingly more specific here. Well, we got close. We almost did it. Now, something I have noticed too with behavior cloning is, and this is from past experience with these kinds of things, if you don't have good examples of recovering, it's not always good at trying to do the task again. You've got to have actual demos in the data set showing the robot, failing at the task, but then succeeding afterwards. Or maybe not failing, but maybe starting from another position that shows it that it can still succeed. Oh, and we got through our 50,000. So let's try one more time, and if this doesn't work, then I'll go run it for 100,000. Okay, not happy with the performance. Let me go and I'm going to do one test live here. And we are going to go to a batch size of 64. So we're going to up the batch size just a little bit, and we're going to go for a full 100,000 epochs. And see how low we can get loss. And while this is just kicking off, I'll show you what it looks like in the first few, because it's obviously going to be very different. Oh, that's being successful, and it's being successful quickly. I wonder if those 64, batch size of 64 was the answer. We're not letting go. Come on, robot. Let go of the cup. If this was a waiter robot, it would be failing right now. It would be refusing to hand the customer their drink. Okay, we're at 3,100. Okay, we have regressed slightly. This is where I'm going to pause and let a bunch of episodes run and come back in a few. All right, I made a couple of tweaks here. So I did go back to a batch size of 32 because at a batch size of 64, it didn't seem like we were really making any progress anymore on lowering loss. And then I came in here to the agent.train method, and I pulled this section where we're checking for something a lot lower than lowest loss. And through that save checkpoint every 10 episodes. So now we have an opportunity on all of the in-between episodes, or some of the in-between episodes, to grab a checkpoint, every 10 steps instead of every 100. So let's see how it's doing. And again, I had to restart training, so we're only about 20,000 in. And that was much more successful. Let's just make sure that we're being consistent, which we probably aren't at this point. Like, it's still training. Oh. So it got it on there, but the task didn't quite register as successful. But honestly, that looked a lot like success to me, even though it doesn't know how to recover. Let's try one more time. And we are successful. So 3 out of 4 times full success, 1 time not quite getting onto the plate. And again, with those couple of tweaks, we reached that around 26,000 epochs with our batch size of 32. So that is the entire project. We set up an environment, we pulled down data sets, we used those data sets to do behavioral cloning on a task, and then we were able to successfully watch the robot actually go and execute that task, which is a really cool place to be. Let's talk about next steps. So, like I said, this project wasn't intended to be, a be-all, end-all of behavior cloning. I am building it as a kickoff on the road to go figure out how to do things like VLAs, and vision language action models frequently lean on behavior cloning under the hood. So this was kind of my just starting to play around with behavior cloning project. Things that you could do to extend it would be to extend it to multiple tasks, and figure out how to load in, different tasks for the robot. Can you get it to complete more than one? Can you get it to, like, what happens if you feed in joint states as well as images? We did this with just images, but maybe joint states let it train faster. Maybe they let it train more slowly. Pass in different sized networks. I started off with 256 parameters and it worked out of the gate. Play with fewer, play with more. Add better logging. There's a lot you could do with this project and kind of build it up into your own and learn more through the process. But hopefully this has been useful to you. This was not kind of my normal format. My normal format is building up a much bigger project and kind of doing, a little bit more upfront to explain what we're doing. This was just kind of barreling through building something. So let me know what you think, if this format works for you. And until next time.